Do you have our test?
I'm sorry, I don't have your test. I'll have it
Dr.
tomorrow,
Chappelle, you
though.
always tell us one thing. And
I know.
Disappointment.
I'll have it tomorrow. I know. I knew you guys were going to be disappointed. What did you do for this? Did you put it
NNO.
NNO or NON?
NNO.
NNO.
How come you did NNO?
Because N is more electron. And
Least electron. That's not always the case. Sometimes O goes in the middle. You know, for example, in compounds like this is dimethyl ether. And O bridges the two methyl groups like this. And so there are cases where O goes in the center, you know, even though it isn't the least electronegative in this case. And so we do this, and then we complete the octets to the outer atoms. So that gives us 16 electrons. And then we're going to do what next? Yeah, we got to make an octet for nitrogen. You know, we got an octet for this nitrogen, but not this center nitrogen. The center nitrogen is missing some electron density, so we want more. And so who's going to sacrifice some electron density?
Nitrogen.
Yeah. Well, nitrogen versus oxygen, we expect nitrogen to.
Why?
Why?
Yes.
Oxygen is more electron.
Oxygen is more electronegative, and so nitrogen is going to be easier to take electron density from, as being less electronegative. And so we end up with a structure that looks like this. All right, now
It's still
short. Yeah, we're still short. And so who should we take it from? We just took a pair from nitrogen. Now should we take a pair from oxygen to keep it fair, or do we just keep taking it from nitrogen?
Take it from nitrogen.
Take it from nitrogen? How come?
more electronegative.
Okay, but it did lose some electron density already, but we'll go ahead and take it from nitrogen. And we end up with this structure here. Maybe I'll write it over here. And so we end up with a nitrogen-nitrogen triple bond. Going to something like this. Yeah? Is this structure okay? Well, from an octet point of view, all these structures, actually this is not okay. This structure is okay. This has an octet, this has an octet, that has an octet. So everything has an octet, which is good. But something looks weird about this. What is it?
Formal charge.
Yeah, the formal charge. What are the formal charges going to be? This nitrogen, 1, 2, 3, 4, 5, 0. Plus 1, minus 1. And so if we try to get rid of that formal charge, we aren't going to be able to do it. And so essentially, when we look at a structure like this oxygen is pulled an electron away from nitrogen, let's say. So nitrogen came out short of 1, oxygen came out ahead of 1. Is that okay? Well, it's okay in the sense that oxygen is more electronegative. Well, what would have happened? You know, rather than doing this, to go choice 1, rather than doing this, what if we pulled the electron from the oxygen instead? You know, what difference would that have made? So if we took this, which is choice 2, we would have generated a different structure. This structure is going to look like this. Where we have a nitrogen double bonded to a nitrogen double bonded to an oxygen. Lone pair. And then 2 lone pairs like that.
Why doesn't it still have 2 lone pairs on the
Oh, it does. All right, how does this look? This looks good too because everything has an octet. But what about the formal charges?
Plus 1, minus 1.
Okay, we're going to have minus over here and plus here and 0 here. So now compare the two structures that we end up with. Yeah. If we compare the two structures, what's the difference between the two structures?
The pole is equal between the nitrogens.
Well, one, this is more symmetric because we got a double bond and a double bond, right? So it looks more symmetric. But, you know, that doesn't matter, really. We don't have to have it symmetric. It's already asymmetric because we got two nitrogens and then an oxygen, rather than a nitrogen, oxygen, nitrogen.
Isn't that one wrong because in the tug of war between the nitrogens,
Well,
there would be that charge distribution?
yeah, you're right. This is kind of weird because the tug of war, but in a way, it's not weird because look at this nitrogen.
Yeah, it's the same thing.
It's the same thing. And so when we're typically talking about tug of war, you know, this is actually a tug of war not between the nitrogen, because nitrogen is going to come out a loser either way in both structures, right? This is actually a tug of war between what? Nitrogen and oxygen. The tug of war is for this extra electron.
Why?
Because if you look, the extra electron is on this oxygen here that gives it a negative charge here, and the nitrogen break even. In this structure, now the extra electron is on nitrogen, and this oxygen's break even. And so the tug of war is between these two outer atoms. They're fighting for the electron. And so maybe neither of these looks great. Maybe we should have tried the other skeleton, you know? And so let's say, what would have happened if we put oxygen in the center? Could we have gotten a better structure out of this? And so let's try oxygen in the center. Okay, once again, oxygen doesn't have an octet, so what do we have to do? Yeah, in this case, which nitrogen do we pick?
Either one.
Either one. So let's take this one. So we do that, and we get a double bond here. Oops. That. But it's still not complete. And so what should we do? Should we take another lone pair off the same nitrogen or the other nitrogen? Here it makes no sense to take it off the same, and we'll take it off the other. And so now we got two double bonds. It's got to be symmetric, right? Because the nitrogens are both the same in this case. The other one could be asymmetric. Looking at this one though, this one looks weird too, right? And so what's weird about it? It's not the octet, that's not weird. The formal charges. So let's calculate the formal charge. Here, minus, plus 2, minus. What do you think about this formal charge arrangement? It looks balanced. Does it look okay to you? Yeah, this does not look okay to me. Why?
There's no way the nitrogen can bounce electrons away from oxygen.
Right. Basically, this means that each nitrogen attacks the oxygen and takes an electron away. And think of the first ionization energy, okay, maybe. But the second ionization energy? No way. Not only that, is nitrogen more stronger or no, it's less strong than oxygen. So, you know, this looks even worse. So if we tried to put oxygen in the middle, we would have gotten a much worse structure. But sometimes it's worth a try because, you know, we could have gotten a better structure with a different skeleton. And so we got to try it and see. All right, now it boils down to these two structures. And which one do you like better, the left one or the right one, and why?
The left one doesn't make sense for the oxygen to have.
Yeah, it makes sense because if there's a tug of war between these two outer ones, which one should win? The oxygen. Oxygen should win. And therefore, this should be the most stable structure. But you have to ask yourselves, we're seeing things in black and white here, you know, where there's a winner and there's a loser. Oxygen's the winner, nitrogen's the loser in a tug of war. But if you consider their strength, oxygen is a 3,5, nitrogen is a 3,0. They're both very strong. In fact, what are the three most electronegative elements on the periodic table? Yeah, fluorine, oxygen, and nitrogen. And so oxygen and nitrogen are comparable in strength. Sorry, let me turn this on. Oxygen and nitrogen are comparable in strength. So is this going to be a total lopsided victory for oxygen? No. In fact, what would you guess? You know, about how much weaker is nitrogen than oxygen? Not much. What do you say? If this were even, and the oxygen and nitrogen were equal in strength, then this extra electron wouldn't be on oxygen, it wouldn't be on nitrogen, they just split evenly. And so if this were even, we get a minus 1/2 on oxygen and a minus 1/2 on nitrogen, and we had two resonance forms which give us a hybrid where it shares evenly, right? But we know that nitrogen's weaker. How much weaker would you say? Let's take a guess. 0.3? Okay, if nitrogen were 0.3 weaker than oxygen, then oxygen wouldn't win the whole electron. In fact, what would happen here is oxygen would end up with, well, what we have to do is we have to do a hybrid. And you know what these two are? These two are inequivalent resonance forms. You know, when we have equivalent resonance forms, we just take the average of all of them. When we have inequivalent resonance forms, what we do is we do a weighted average rather than a straight average. And so the hybrid will be a weighted average. What is a weighted average? A weighted average is, it's not a 50-50 mix. It's going to be, well, which one's more stable? The left one. And so let's say this one's 70% more stable. Actually, let me go with 80. Let's say this one's 80% more stable than this one. This is 20%. And so what we're going to do is we're going to do a hybrid, but the hybrid is going to be biased towards the left structure. And so in our hybrid structure, this is what it's going to look like. We're going to have an N and O. We're going to have a double bond that never changes, and a single bond that doesn't change. Then we're going to have a lone pair here that's always there, and two lone pair on oxygen. They're always there. But what happens is this. If this structure is biased, the double bonding electrons, I mean not double bonding, the extra bonding electrons here spends most of the time here, 80% of the time here, and 20% of the time here. If it's 80% of the time here, then what we call this is a 2.8 bond. You know, not quite a triple bond, but more than a double bond. And then over here, we're going to call this a 1.2 bond. 0.2 bond. Stronger than a single, but not as strong as a double. And then the lone pair is going to be floating. 80% of the time the lone pair is here, 20% of the time the lone pair is here. If the lone pair over here is 80% of the time, then the charge over here is going to be minus 0.8 for 80% of 1. Over here the charge is going to be minus 0.2. This is for an 80-20 hybrid. If we did a 70-30 hybrid, what would we get? Yeah, if we did a 70%, 30% hybrid, then this would be this would be 7, and this would be 1.3. That would be it. Why did I choose an 80-20? One, there's a 5, you know, 3.5 versus 3. 5/30 is about 5/30 is 26. 1/6. 1/6 is 20%. 1/3 is 1/6 is what? Well, is it 13%? 1/6 is
13.
It's like 18.
18%. Something like that. So this is why. And the second reason why is, this is a guesstimate. This is a guesstimate. This is a guesstimate based on, the differences in electronegativity. That's it. But if we actually do the quantum mechanical calculation, do you know what the charge comes out to on oxygen? About -0.8. So that's why I picked it. And I already knew what it is. So anyway, this would be the hybrid structure, and this is a more complicated hybrid structure because we have inequivalent resonance forms. You see that? Electron density. And these resonance forms can interconvert from, well, if you think of them as resonance, because what we could do is pull these electrons out, put these electrons in, go back and forth, or throw these electrons back in, and then pull these electrons out. But in reality, it's not doing that. In reality, it's just spreading out. And this is how it's going to spread out. Does that make sense? A little bit? Okay, so that's a complicated resonance hybrid. Uh-huh.
So what makes it
Okay.
So what makes it in equivalent resonance form again?
Inequivalent, they aren't the same exact energy. That's all. One's higher in energy. We saw this before. Remember this? Bicarbonate? But the thing is, this one is so unstable compared to the other two that the percentage of this is very small, that I completely ignored it. So we ended up with two resonance forms for that. Whereas, is it really a huge difference between oxygen and nitrogen in terms of electronegativity? No. They're close. And so there's less significant difference between the two structures we just looked at versus this. This is a huge difference because here we're going, look at positive on this oxygen, negative on these oxygens. Is that stable? No, not even close compared to the other two. So this one is such a minimal or negligible contributor that we don't even have to consider it, even though this would be an inequivalent resonance form.
When I pushed you off the last example, I did it for the bit structure as opposed to a linear one. I just was wondering why would it be linear even though
What?
I'm sure it's pairs.
Why would it be linear? Because you're looking at this middle atom here. It doesn't matter what the terminal atoms are doing. It matters what the middle atom is doing. So let's take a look at the structure. The structure is linear. You know what the bond angle here is?
180?
180. Are the two bonds the same? No. This one's shorter and stronger, this one's longer and weaker.
Oh, the angle is exactly 180?
The angle is actually 180.
What is that called again?
It's called valence shell.
Yeah, linear.
Oh, linear. Okay, and so look, now let's go to geometry, molecular geometry.
Yes. Is the resonance forms in the book as well?
Resonance forms? Yes.
The hybrid too.
Oh, that's
The hybrid is in the book, yeah.
Okay.
The inequivalent resonance forms? No.
No?
No. It's in the homework, though. This is a homework problem.
And like a non.
It's in the book, but it's not in the. This is how you know how you make an advanced problem. You don't talk about it and you throw it in the homework. That's how you make an advanced problem. But if you talk, you know, this is an advanced problem. Yes, it is an advanced problem, but
That was my question, because sometimes when I'm doing those problems, I feel so just dumb.
that's why you have other books, because maybe in another book they talk about this as an example. That happens all the time where you go, you know, this problem's so out there, I have no idea. And then you go and you look in another book and they spend 2 pages talking about it and they go, oh, it's so easy, you know, after you hear after the fact, right? It's so easy, right? So this is why when I was studying, I always looked at, I was always at the library looking at other books.
Which book would you suggest to look at the resonance hybrid?
Resonance hybrid? I would go online, look up nitrous oxide. Go online and look up nitrous oxide. This is the classic example of inequivalent resonance forms in this funky hybrid. Nitrous oxide is everybody uses nitrous oxide. And so it might not be in our book, but it's in plenty of other books, and it's in online and in the literature all over the place. So it's out there, you can find it, you know. Nitrous oxide's in our homework though, so you'll see it. Well, let's talk about molecular geometry next. Whenever we deal with molecular geometry, we have to look at the electron geometry as well. And so molecular geometry is somewhat based on the electron geometry. But really what we're after is, what we care about is molecular geometry. Electron geometry is just something we have to go through in order to figure out what the molecular geometry actually is. And so as far as electron geometries, let's take a look at them. We have a linear electron geometry. Electron geometry would just be, you have a central atom here, you could have 2 single bonds, like this. Or you could have a double and a single, or you could have 2 doubles, or you could have a triple and a single, like we just saw. You know, these are all linear electron geometries because we've got a triple bond on one side, a single bond on the other. It's just in a straight line. And so an example of this would be nitrous oxide here, or carbon dioxide. That would be a linear electron geometry. And we can see it here. We have the central atom, the double bond here, double bond here. It's linear. For molecular geometry, we look at the bonded atoms only. And so for the bonded atoms, it's going to be linear here. And so the molecular geometry is linear, just like the electron geometry. Linear. And again, molecular geometry is just for the bonded atoms. Bonded atoms only. All right. Well, what do we want to know? We want to know the bond angle. Now, the bond angle here is defined by 3 atoms. The oxygen, carbon, oxygen angle is 180 degrees. And we want to know the bond lengths. The bond lengths we look up in the table. How long is a carbon-oxygen double bond? You can find that information in the table. That's linear. The next electron geometry that we're going to encounter is trigonal planar.
What symbol is that?
Which symbol?
Is that an angle symbol?
Yeah. This one's supposed to be angle. And so trigonal planar, we could have 3 single bonds in this triangular arrangement, or we could have a double and 2 singles, like in formaldehyde, or we could have a lone pair and 2 singles, etc. So these are all examples of a trigonal planar. Normally, the angle between these groups here, electron, is 120 degrees, right, all the way around. Why is it 120? It's 120 to minimize the repulsions between electron clouds. You know, electron clouds have negative charge density. And so we try to minimize the negative repulsions by spreading them out in space as far apart from each other as possible.
Okay, so what's the difference between trigonoplanar and trigonopyramidal?
Trigonoplanar is flat, like a pancake. Trigonopyramidal sits up.
It's a form of tetrahedron.
Yeah.
Okay.
They're like this. Trigonoplanar would be all in the plane, so this is not trigonoplanar, you know. This would be trigonopyramidal. We'd have to squish up.
1D and 3D.
Yeah.
Are we going to play with the model?
Yes. Right.
Does the angle change when there's a double bond?
Right. The angle does change when there's a double bond, because a single bond, you know, you got a certain electron cloud and it requires a certain amount of space. But now if you have a double bond there, there's going to be more electron density there, you know. In fact, you're going to have twice as much electron density. If you have twice as much, then the electron cloud is quite a bit more dense, you know, or bigger. And so what that does is it's going to cause some greater repulsions here. Because of the greater repulsions, the angle actually widens here. And so what we say with the angle here is it's greater than 120 degrees. Typically it's around 122, so it's slightly greater than 120. And so this angle is greater than 120. What about this angle?
Less than.
Greater, actually. And this one's going to be less than 120. Well, now what if we have a lone pair? Well, if we have a lone pair, then a lone pair behaves like a double bond. And the reason why it does that is because when we have a bond, let's say an AB bond here, there's a tug of war. A is trying to pull the electron density, B is trying to pull the electron density. So the electron density gets spread out between A and B. But when we have a lone pair, there's no tug of war because nobody's pulling on the electron density from the opposite end. And so all the electron density gets concentrated on the atom A. And so it turns out that this creates an electron cloud similar to a double bond here. And what that's going to do is it's going to widen this angle. But this angle we don't consider as a real angle here. This one. Nobody will quote you on this angle because of the Heisenberg uncertainty principle. What does the Heisenberg uncertainty principle say? Yeah, the exact electron position is, well, somewhere in here, right? I mean, if you have an axis here, then yes, the angle can be quoted as greater than 120. But really what we can measure is there a Heisenberg uncertainty principle for the atoms? Can we pinpoint atoms? Yeah, we can pinpoint atoms. So we can pinpoint 3 atoms, C, A, B. We can pinpoint those, but we can't pinpoint electrons, lone pair A, B. And so the only angle that we're going to measure is this angle here. That angle. And this angle is less than 120 degrees. What would you guess? If this were about 122, that means this angle must be about 116. This is about 116. You know, it wouldn't be like 100 degrees. You know, that would be hugely less than 120. And so, let's take a look at some examples of this right now. We can look at formaldehyde. This would be for molecular geometry. For molecular geometry, we look at the bonded atoms again. And so when we look at formaldehyde, I know looking at this carbon here, the electron geometry is trigonoplanar, but when I look at the bonded atoms are also in a trigonoplanar arrangement. And so we call this the trigonoplanar molecular geometry. If we look at another example here, let's look at BF2 minus. BF2 minus. Boron is a little bit unusual. You know why? Because does boron have an octet here? No, it doesn't have an octet. And so really we should make a double bond, right? We should make a double bond. But there's a rule. And the rule is fluorine never, well actually hydrogen and fluorine never form, let me put an asterisk there, never form more than one bond. The reason is, what is the formal charge on this fluorine here? Actually 0. 1, 2, 3, 4, 5, 6, 7. 0. What is the formal charge on this one? +1. What is the formal charge on this boron? Actually, actually it's -1. This is all negative here. This is negative. So basically, you have this. Now what is the formal charge on this? It's 2 negative, and this is plus. And so essentially, if there's a tug of war between fluorine and boron, who won? Boron. Boron took the electron from fluorine. Does that make sense? Not at all. Now, fluorine being the most electronegative, this is never going to happen. Therefore, fluorine's never going to lose electron density by forming a multiple bond, because each time fluorine forms a multiple bond, its formal charge goes up 1. In other words, it becomes more positive. Well, anyway, we see that this has a trigonal planar arrangement of electron groups. That is, we have a lone pair and 2 bonds here. But looking at the molecular geometry looks like this, which we call bent. Bent. And the FBF angle, what would you expect? Less than 120 degrees. Less than 120. The OCH angle here is what? The OCH angle? No, greater than 120. The HCH angle? Less than 120.
Why is it less than 120 for the,
Because they have to add up to 360.
not right there, but the other?
Because the lone pair takes up space. This lone pair here takes up space and pushes these other electrons in. All right, we'll stop here. We're going to take a look at some more molecular geometries tomorrow, and we're going to work with some models as well.